Okay, now we move on to multivariate regression, but before that, we need to talk about some concepts here. And this can get very theoretical, but we're not going to go into all of the details. For more details, you can click on this link and you can read more about F statistics. So let's start out reviewing some of what we did before. Bootstrapping again is sampling with replacement, and then we can evaluate the means of all the different realizations we got from bootstrapping. So you now have multiple means for each bootstrap sample, and that is what we call the bootstrap mean. That's just reviewing what we did before. But now there is a population size, right? Remember, there is a difference between a population and a sample. So all of the data set constitutes the population, which is of size n. Sample is a subset of that, and sample size is small n. Now, first definition of term, standard error. The standard error of the mean, written as SE, is simply the ratio of the standard deviation of the sample. So standard deviation of the entire population is sigma. Standard deviation of the sample is S. And divide that by square root of sample size, and that's your standard error. So standard error is just some normalization of your standard deviation, and the normalization is simply by dividing by the square root of n. Degrees of freedom is equal to sample size minus 1. So DOF, which is degree of freedom, is simply sample size minus 1. T statistic, which is the test statistic, is your sample mean X minus population mean mu divided by the standard error you got from here. So simple definition. And we can use F statistics to decide whether or not to support or reject null hypothesis, like we talked about using p-value with the null hypothesis. And without getting into all of the details here, which you are advised to read many times, all we have is the critical F value. And when we have that, which is also called F statistic, you just need to pick the model with the highest F statistic. So the F statistic is the same as the critical value. So the bigger it is, the more statistically significant is your model. So your model is more accurate when the F statistic value is higher. And you will see that in the examples. And we went through all of these so that we can compare different multivariate linear regression models. So now let's go into the multivariate linear regression models. It just means you're going to be using more than one exploratory value. As a reminder, this is what we did the last time. We only used QMOL as our X, so one column, and your Y is also one column. Now, X is two columns. We've added in Gassel ratio as a second column. We'll put it in the first column. And we're plotting it against Y, or we're doing the regression of X against Y. What do we get? Everything else is pretty much as we had in the previous code above. I don't need to scroll there again. And this is the model summary. R squared value actually drops, right? Let's not guess. 765 r squared, adjusted r squared 75.3. So r squared went up a little bit by 0.001, but adjusted r squared went down. And I said adjusted r squared is important for multivariate regression, and that's precisely what we're doing here. So why did it go down even though r squared went up? In general, anytime you add more variables to a model, r squared tends to increase. But it doesn't mean the model automatically gets better. It just artificially increases. So to correct for that increase, we adjust r squared value. And that's why it's called the adjusted r squared. And it's been adjusted so it's lower. So this is actually a worse model. So for multivariate linear regression, you always want to use the adjusted r squared value instead of the r squared value. R squared value is artificially increased just because you have more variables. And many times, more explanatory variables means more complex more complex regression, but it doesn't translate to a better model all the time. So, moral of the story is you always want to use the adjusted r squared value instead of the r squared value when working with multivariate linear regression. There are other parameters that are also important here. F statistic, which I talked about before. The bigger it is, the better. So which one is bigger? It's 29 here. It's 61 here. So this is better based on the F statistic. Also based on the r squared value. The adjusted r squared value, the single variable model, the bivariate model is better than the multivariate linear regression model. This is also very important, the p-value. It's high here, so this term which we added for the gas-oil ratio is actually not doing much good. You want p-value to be less than 5%. This is 78%. So more complicated models sometimes doesn't necessarily mean you have a more accurate prediction algorithm. Another point worth making here, I'll make it later so you see all of these commented out. Yeah, this is how you add a constant term to your regression, and I'll talk about it in the second example. But I realize these models are more accurate in terms of the adjusted r squared when you don't add a constant term to the linear regression equation. What if we add a third predictor? So we added GOR on the previous code. Now we are also adding water depth. Again, r squared value will generally increase, but adjusted r squared value doesn't necessarily increase, and that's precisely what we see. R squared went up. It was 76.6. Now it's 76.9. But adjusted r squared even went down. So this is even a worse model than the previous one, which is worse than the bivariate linear regression model. F statistic also went down. Again, you want F statistic value to be high. So the smaller it is, the worse is your model. P-value, again, for the new variable we added in, is high. It's more than 5%. So we've added two variables that really bring nothing to the table. So these are more complicated. This makes the model more complicated, but it's not cutting it. If you choose to uncomment this, and I recommend you to do that so that you can add a constant term to the regression equation, this is what it looks like. So the constant term you add basically just puts in a 1 here, and that gets used to calculate the constant coefficient, so beta naught, in the equation from the previous slide. Let me jump to it here so everything is in context. I have the equation written out here. Yeah, so remember this equation, right? This is for multivariate linear regression. First exploratory variable, second exploratory variable. This is just an error which we don't care about for the purposes of this illustration. But this is the important one. It's the constant term. To calculate this constant term, which isn't part of your model parameters, you need to have 1 instead of the x's. So added to the x's, and that's what we have done. So the x's are these guys, GOR, QMOL, water depth. We've added a constant term, which is all 1, so that the model can now estimate the coefficient. And let me comment it out just very quickly and run it so you can see what it does. So we've added it to it, and now you have the constant term here, and this term right here is your beta naught, and this is beta 1, beta 2, beta 3, and that's how it works. But the adjusted R squared values are much lower, which is why I commented it out. It doesn't mean you never want to use the constant. Every time, many times you need to use the constant, but in this case, it just turns out if you don't provide the constant term, meaning intercept is 0, right? It becomes more accurate. So what I mean by intercept being 0, again, if I jump down here, if you remove this term, it means you're saying the y-intercept is 0, and the other terms just add up to it. So for these cases, in this spreadsheet, in this lab notebook, you're better off with beta not being 0, but give you the code that allows you to either set it to 0 or have the regression model make the estimation. And that's precisely how you do that. So I move on now to try a different concept. We added GOR, the model got worse. What if we add log, natural logarithm of gas oil ratio instead of GOR? So we take the natural logarithm of all of the data and add that in to our X and do the regression again without the constant term. And this is what you get. It's when R squared value increases, but adjusted R squared is still worse. Before it was 75.3, if my memory is any good. And so it's still worse than the bivariate linear model. P-values are here. This is not adding much value. It needs to be less than 5%. And this is the coefficient, beta naught, which is actually beta 1. It's going to be multiplied by the log of gas oil ratio, and this is beta 2, that will be multiplied by the second exploratory variable, which is QMOL, and there is no constant term. So that's how you interpret these results. Another data set, magnesium and calcium content of water. And this is the electrical conductivity of water. So put that into a data frame using this function, which we've used over and over again. You get this: magnesium content, calcium content, electrical conductivity of water. And we are assuming these two influence the electrical conductivity of water. We can do the descriptive statistics calculation using the describe function. Compare plot the 3 variables. On the diagonal, you have the same variables, so we get the histogram instead. And this is showing the second variable is strongly related to conductivity. This also is related, but not that strong. And this is the relationship between the second and the third variable. So if it's very linear, then you're seeing a strong relationship between your exploratory variables, meaning they are not independent. And we don't see too much of that here. This is the first order model again. Two variables, magnesium and calcium content. Here I'm using the constant so I can calculate beta naught. And when you do, this is what you get. Very high R squared and adjusted R squared. This is the number we care about, right? 96.7. We can grab those model parameters, which are precisely beta naught, beta 1, and beta 2 in the previous equation. And you will see that's precisely this. So this column gives you the coefficient, 0.2407, 0.2407. What if we want to create a higher order model like we talked about in the slides? You see, this is x squared. So these are the quadratic terms, right? X1 squared, x2 squared, quadratic terms. How about this? What term is this? It involves the interaction between x1 and x2. So that is the interaction term. How do you implement this? You will still implement it just like your linear regression, except that instead of providing x3, so basically this term you will make it your x3. So x3 is x1 squared, x4 is x2 squared, x5 is x1 times x2. So at the end of the day, it just looks very much like your regular multivariate linear regression, and this is precisely how you do that. First two terms as usual, x3 we make it magnesium squared, x4 calcium squared, x5 is what? The interaction term, magnesium times calcium, and all of that goes into dfx. We add the constant so we can actually capture this term and have it estimated. If you don't add it, if you comment out this line, then you're assuming intercept is 0. But because we don't make that assumption, we can run this, get these results. That's your constant term. And when you do the regression, you will have the coefficients beta 0 through 5 corresponding to these 5 terms, beta 0 through beta 5. And we can grab the summary. Adjusted R squared went up 97.8. Of course, R squared also went up, but the important thing is adjusted R squared is 97.8, which is better than 96.7. F statistic is 218, 131. So it's giving conflicting information, right? Because you always want the higher F statistic. So which one do you choose? Always go with the adjusted R squared. It's more important than the F statistic. So which parameter contributes the most to the electrical conductivity, which is your dependent or response variable? This one is the one with the lowest p-value. And if we were to remove or eliminate one of these variables, which one will we eliminate? The one with the highest p-value. So we'll remove this, which is 86.5%, meaning we remove the first column. And that first column is magnesium. If you run that, you find out which one also has the second highest p-value. And you also remove that, and you can keep doing that in a backward elimination method, which we'll be talking about when we introduce the Lab 10 workbook. And with that, I'll stop this video.